Hi everyone, my name is Claire Yin and I worked with Pedro Colon-Hernandez and Henry Lieberman at MIT CSAIL and the MIT Media Lab. So there's a lot of exciting work with large language models and they can perform well on NLP tasks, but a lot of these language models are lacking common sense knowledge. And so our research proposes getting help from the neighborhood. We use the idea of convolutions from computer vision to perform local semantic averaging on common sense knowledge graphs to improve common sense knowledge in these language models. So overall, to understand language, there's two aspects of text. There's the syntax and there's the semantics. So the syntax includes the sentence structure and the grammar. Meanwhile, the semantics is the actual meaning behind the text. So most times the syntax is explicitly in the text and the semantics are implicit. So this is where common sense knowledge lies. Semantics. And research has shown that these language models, when performing these NLP tasks, use both the syntax and the semantics of the text that it sees. However, this research also shows that sometimes these language models can produce false information, hallucinate these like false semantics based on the text. And this results in a lack of common sense knowledge. So here's an example. Let's say our input text is a dog is a mass token. If we give this input text to Bert, Bert responds with a dog is a dog. Technically, this is right. Technically, dog is literally the most similar thing there is to dog. But when we bring in our common sense, we know that a dog is a dog, but we also know that this is not the best answer. A dog is a pet, a dog is an animal, a dog is a loyal friend, etc. So in order for our language models to be able to learn concepts like this, we need to make these concepts explicit rather than implicit. So we can do so using common sense knowledge graphs. And these graphs basically encode entities along with labeled edges that represent the relationships between these entities. So for instance, we can see that a dog is an animal. We see that humans are also animals. We see that humans own dogs, dogs are loyal friends, humans are alive, etc. And this is all common sense knowledge that we sort of take for granted, and it's not really made explicit. We don't see it in, textual data usually. And when we're communicating with other humans, we sort of anticipate that they have this common sense knowledge as well. So if we want to communicate better with our language models, we need some way of making this common sense knowledge explicit. And the specific knowledge graph that we use in our research is ConceptNet, which some of you may have heard of. It's basically a collection of over 21 million relations between over 8 million entities. And in the English subset of this data set, I think there is about 1.5 million assertions. So assertion is, for instance, a dog is an animal. So here's an excerpt of a knowledge graph that they have on the ConceptNet website to further describe ConceptNet. So I took a little snippet of that. So ConceptNet is a knowledge graph which has common sense knowledge, and this common sense knowledge is a part of building AI. It's also a semantic network, so again, it encodes these, the meanings, the common sense knowledge. And it's made of crowdsourced knowledge and used for natural language understanding, and it's also used to build these meaningful word embeddings that are used to understand language in AI and NLP tasks. And it's important to keep in mind that ConceptNet is a sparse graph because it's hard to make all of these relationships explicit. The scope of common sense knowledge is very large. So in order to learn from this explicit common sense knowledge, we need some learning model. And here is where I present to you relational graph convolutional networks. So RGCNs bring in the concept of convolutions from CNNs and computer vision. And CNNs pull together information from neighboring pixels to gain context for images. In the same way, RGCNs pull in information from neighboring entities in a graph to create these enriched embeddings. And RGCNs, in comparison to regular GCNs, can also harness the information stored in the relationships in these labeled edges. So now that we have, so let's say we have the same example from before, we're able to enrich our embedding of the dog entity using the neighboring entities along with the corresponding relationships. So now that we have this model to learn from our common sense knowledge graph ConceptNet, we need some way of measuring how well it's learned this information. So we use link prediction. So again, given the graph from before, we have all of these explicit relationships. And we want our RGCN to be able to predict relationships that might not already be there, such as a dog is alive. And we want it to maybe not predict things like a human is a dog. So I'll give a little more detail into the process of link prediction. So we have our input graph ConceptNet, and we perform edge sampling to get some subset of ConceptNet to learn from initially. So we want to feed in our node embeddings along with our relational embeddings into our encoder. And our encoder is just RGCN layers, and in each of these layers, again, the RGCN pulls in information from neighboring nodes along with the relational context to create more enriched embeddings for each of our entities. And this gives us mixed node embeddings. These node embeddings that we started with are now enriched with this relational information and also this neighborhood information. And we also have embeddings for each of our relations that we have learned. And this provides, again, more context. So when we're actually performing our task of predicting links, we can feed these embeddings through our decoder, which is just a dis-molt model, basically performs a trilinear dot product. And so let's say we have two entities, dog and cat, and we want to predict, are there any relationships between them? So we take our embedding of dog, and then we take some embedding of some relationship R, and then we take our embedding of cat, and we feed them through the decoder, and the decoder scores this relationship, this triple, and returns some score on how likely it is that this relationship exists. So we can do this for, like every single relationship possible between dog and cat. We can do this between any pair of entities, and our decoder will return a score. And ideally for things that are like dog is alive, we want a really high score. Things like human is dog, we want a really low score. And so now we have this task for RGCN to perform, and now we need some baseline models to compare RGCN to see how well it's learned this common sense. And so for our baseline model, we use a standalone GCN, which again, in comparison to RGCN, does the convoluting, does the pooling of information from neighboring nodes, but cannot encode these distinct relationships. So it lacks that extra context. And then we also built just a single relation RGCN as an intermediate step, which we expect to perform the same as RGCN. And we trained on 3 subsets of ConceptNet. There's train 100K, 300K, and 600K. And we weren't able to use the entirety of ConceptNet due to computational constraints. So we just used these 3. And here are the results. So top values between the baselines are in bold, and we see that they perform about the same. There's no significant difference across all the metrics. And then the overall top values are underlined. And most importantly, we see that the RGCN does outperform the baselines across all of the metrics. And our metrics are accuracy, AUC, precision, and recall in terms of correct and incorrect triples that are predicted. And then we also use mean reciprocal rank for the RGCN, which is basically a commonly used metric when the model returns a list of ranked outputs. And because the RGCN is the only model that's able to distinguish between relationships, we can only measure MRR for that model. So now that we have these embeddings, these enriched entity embeddings from RGCN, obviously they have additional context that allows them to perform this task better, What do we do with these embeddings? So we want to use them to enrich a language model because, again, our end goal is to improve the language model's performance on an NLP downstream task. And for our specific language model, we use BERT. So BERT has an attention mechanism and also uses the encoder from a transformer architecture to create these effective contextual representations, and the context is brought in from the entire input text. And in our specific case, we use BERT base uncase, which is the standard BERT model. And so now I'll describe a little bit more about the BERT architecture. So we have our input sentence and we tokenize it and then produce embeddings for each of the tokens. These embeddings are then fed through each of the attention layers. Again, these attention layers bring in context to create contextually aware embeddings of each of these tokens. Afterwards, these embeddings are pulled together. They're averaged to create a representation of the entire input text. And then this representation is passed on to the specific task, which comprises of a linear layer and a task loss layer. So now I've set the scene. We have these RGCN embeddings that are enriched with the neighborhood information, the relational information, and we also have our BERT architecture. So the big question is, can we actually use these RGCN enriched embeddings from these knowledge graphs to improve BERT's performance on a downstream task? And to answer this question, we take the following approach. So again, we need some way to combine RGCN and BERT. And we do so using 3 different injection methods. So these injection methods somehow inject our RGCN embeddings into the BERT pipeline. So we have input, architecture, and output injection. First is input injection. This occurs earlier during the BERT pipeline. So we have our tokenized text. For each token, we retrieve the corresponding RGCN entity embedding, and then we pass them through a resize layer and we sum them with the token embeddings from BERT, and then these combined embeddings are then passed through the attention layers and the rest of BERT. And because we're adding this common sense context early on, we're allowing BERT to sort of build the context around that knowledge through the attention layers. And then we have architecture injection. So this occurs later in the BERT pipeline. Again, we take the corresponding entity embeddings from RGCN, we resize them, and we sum them between each pair of attention layers in BERT. So in this case, we're constantly reminding the BERT embeddings of this common sense knowledge that we have produced. And then the rest of the pipeline occurs as usual. And finally, we have output injection. As it sounds, it occurs later in the BERT pipeline. Again, we take these RGCN entity embeddings for each token. We pass them through a resize layer and we sum them, but this time we sum them after BERT has passed the token embeddings through each of the attention layers. So BERT is able to, this is more hands-off because BERT is able to add all the context before, and then we give the common sense embeddings, and then passed on to the task. So now that we have our methods, again, we need some way to measure how well they're doing. So we give our RGCN plus BERT combination the task of Ask Ubuntu. So Ask Ubuntu is a data set of a bunch of Stack Overflow forum posts in the Ask Ubuntu forum. And the idea behind this is we want the model to retrieve semantically similar posts. So a lot of posts might be worded differently, but might be seeking the same answers. And the model does so using some sort of similarity metric. So here's an example of a pair of very semantically similar posts. They're worded very differently. They're mentioning a lot of different entities, but at the end of the day, they both want to know how to install Ubuntu from a USB drive. And we're using cosine similarity specifically as our similarity metric. So ideally, our model would return a similarity score of 1. And again, now that we've set this task for a model to perform, we need some baseline models to compare our performance to. So we take our combination of RGCN and BERT, which we've combined through each of our 3 injection methods, and we compare it to a combination of number batch plus BERT, and we use the same 3 injection methods to combine these 2. So number batch is a set of word embeddings that it takes Word2Vec, GloVe, and Open Subtitles and retrofits them onto ConceptNet. So it not only has, the distributional word embeddings from the other sets of word embeddings, but it also takes in the common sense knowledge that's found in ConceptNet. So we inject these, and it's important to keep in mind that number batch uses the entirety of ConceptNet, so over 1.5 million assertions. And for our RGCN plus BERT model, we were only able to use the train 100K data set because of, again, computational and time resource limits. So we have these 2 combinations, and we compare these to also a standalone BERT model. So this BERT model has no common sense injected in. It relies on the original BERT architecture that we saw. And here are the results of our comparisons. So we see that the top values here between each of the injection methods is in bold, and the overall top values are underlined. And most importantly, we see whether it's the RGCN or the number batch combination, they both perform, everything outperforms the base BERT model across all metrics. And the metrics we use are mean average precision, MRR again, precision at 1, and precision at K. So for the input injection method, we see that RGCN outperforms number batch on 2 of the 3 metrics, and on the third one does not outperform, underperforms but insignificantly. And again, input injection is occurring earlier in the BERT architecture, so this common sense knowledge is sort of sustained through the entire BERT pipeline. For the architecture injection method, we see that number batch outperforms RGCN across all metrics, and same for the output injected methods. And again, we need to keep in mind that number batch is trained or uses the entirety of ConceptNet. These word embeddings incorporate all the common sense found in ConceptNet. Meanwhile, our RGCN method uses train 100K, which is only a subset. So I'll discuss the results a little bit more. So overall, we see the earlier the injection, so for the input injection, the more effective for the RGCN model specifically. And I'll mention this one last time, we're having this common sense knowledge that's injected, and we're allowing BERT to contextualize it through the entire pipeline. So this is a hypothesis for why it might be more effective. And we see that by simply combining a knowledge graph with a language model in any way, by adding this common sense context, we can achieve significantly better performance. And once more, if we were to use the entirety of ConceptNet, if we had the time to do so and the resources to do so, I think we would have seen much more improved results. We see that just for the injection in the input, RGCN does outperform number batch. So perhaps by adding the entirety of ConceptNet, we could see improvements across all of the injection methods. Furthermore, we were only able to try out these 3 injection methods, and for architecture injection, again, we injected between every pair of attention layers, but maybe there's a better way to do this, maybe only using the middle 3 layers, or maybe using the first and the second to last. Maybe there's some better combination, and these could be tested out as future work. Also, we used the Ask Ubuntu dataset for our downstream task, but this is not the most appropriate for common sense inference. This was just what was most readily available to us. So future downstream tasks that could be used on our model include common sense QA. So this is a set of Q&A multiple choice questions that are actually crowdsourced and based off of concepts found in ConceptNet. So this is a lot more directly applicable and could better test how our model actually learned this common sense knowledge. Similarly, SWAG is a set of multiple choice, common sense questions. And similarly, these would probably better assess our model. And we hypothesized that our model would maybe actually perform better on these because they're directly testing what we were trying to do. So in conclusion, we retrieved these RGCN embeddings that encoded ConceptNet and brought in the relational context and the neighborhood context that's found in ConceptNet. And using this common sense knowledge, we were able to improve the standalone base BERT model. And I think there's a lot of potential for this. Obviously, we didn't show improvements across all metrics. We see that number batch outperformed RGCN across a lot of metrics, but just by adding some relational information, we can add context. We do see that. And just by adding some common sense knowledge, we can improve language model performance on the downstream task. Thank you.
Thanks for the talk. Lovely. I completely applaud the objective. Your first example that you say, dog. A dog is a dog. That's not a common sense failing problem, right? That's actually true. It's just stupid, right? It's discourse-wise dumb.
Yeah.
Right? It is not a problem with my common sense reasoning. In some sense, it's a problem. It'd be like if I said, do you know what time it is? And you said yes, right? That's just not, you didn't provide any more information. So it's much more, it seems to me, much more a discourse problem. Can you give me an example of how this actually improved an output? Because I didn't see that, and I'm hopeful that I'm going to be terribly, terribly impressed with what it does that it wouldn't do with a normal BERT model, because you're not doing discourse here, right? That's not what the objective is.
Yeah, I see what you're saying, and I have thought about that. I think it's less that it's more of the fact that if we did have common sense, maybe that answer would be improved, is the lines that I was thinking along.
Well, I wouldn't say common sense rules out a dog is a dog, right?
Right.
That's actually true by common sense, right? It's identity, that's fine. So I'd be surprised if your model actually ruled that out.
Yeah.
So, okay, there you go.
I would love to discuss this after. I can't think of any specific examples, but.
Do you have examples from what you actually did?
I'm gonna need to go back.
Let me just stress that point again.
Sure.
Our databases aren't full of a dog is a dog, a cat is a cat, right? So in some sense, any kind of database assumes that the reason you're asking the question is to get some information that you might not know as the questioner, right? So that's why it's not good to give back the same answer. Now, of course, a language model doesn't have any kind of duplication checker in it or anything that would prevent that from happening. So maybe it's not the best example here, but it was just an example of something where the language model fails because it's not responding to the needs of the person who's asking the question. So one of the things that's very important about common sense knowledge, it's not just any old fact, right? It's a fact. If something is in ConceptNet, the reason it's in there is because humans thought it was important, an important thing to know for solving a wide range of problems. That's why the assertions are in ConceptNet. So if you say a dog is an animal, that's good because it would help you solve a bunch of problems, right? Or a dog is a loyal friend because now if you need a friend, you can get a dog, right? So that's what the kind of thing that we're trying to improve.
Right, but the reason that the dog is a bad answer is because it's a tautology.
Yeah, I mean, we can probably,
causally wrong.
All of us have seen things, examples, other kinds of examples where the language models go crazy, right? Right.
Yes,
and one reason they go crazy is because they're not giving you an answer that would be something the questioner might not know, and that might be useful for problem solving in a lot of situations. So that's what we're after.
Yes.
Okay.
Hi, thanks for the talk. I was hoping you could go back to the results slide from the link prediction. Because you were talking about how you think your performance would improve if you trained on all of ConceptNet. But if I'm not mistaken, I think that it seemed like your link prediction systems performed better on the smaller subset of ConceptNet than on the larger one, whereas GCN did improve as it was using a larger subset of ConceptNet. So I was wondering if you could just riff on that.
Yep. So I've thought about this, and I think that the reason why this happens is because our GCN might need a lot more space and a lot more dimensions to, encode all of these different relational contexts in comparison to GCN, which, might not change in the dimensions, but doesn't have a lot more relational information, relational context to add in. So I think that maybe if we increase the size of our RGCN in between these, maybe it would have outperformed.
That makes sense. Thank you.
Mm-hmm.
Really interesting talk. I had a question about maybe how you were viewing, what you were viewing as some of the purposes of the generation. One of the challenges for these types of large language models that relates to some of these other concerns that people briefly touched on is that they essentially work by bullshitting,
Yeah.
right? There isn't an underlying purpose. There isn't, and you can correct me if I'm wrong later, Will, there isn't an underlying intent,
Right.
For why it's generating. It's just spitting out text to spit out text, right?
Mm-hmm.
And in that sense, right, a dog is a dog there's nothing inherently wrong about it because there isn't a purpose for what it's generating.
Yeah.
How you evaluate, some of these initial examples where you said, well, a dog is not great. A dog is a loyal friend might be better. A dog is an animal might be better. It depends on what your purpose is, whether you're going for fluency or whether you're going for veracity or whether you're going for, being socially appropriate to say, or what have you. And so as you're starting to approach this problem, do you have thoughts as to which of those you are trying to actually get this to your types of models to accomplish?
Yeah, I think that's a really good point. I think that generally these language models, the idea is that they lack common sense, right? They haven't been able to see these implicit relationships, and it might show in different ways. It might show in the sense that they give these answers that are really bad, or they give answers that are not, completely contextually aware. So I think that's more the idea, just bringing in as much context as possible so that these models can more resemble humans.
But so, and just to briefly elaborate there, so is then the goal that the ideal response is going to be the one that best resembles a human response? That is, it's most likely to resemble things that are in the training set, or is it going to be the response that encodes and relates to the most points of common sense knowledge?
At least from my perspective, I think it makes more sense to try to mimic the common sense that's found in humans, and maybe not being, the thing that a human would be most likely to say, but at least grasping those contextual concepts that all humans do have.
Interesting. Thank you.
Mm-hmm.
Okay, we are about out of time, so I'd like to first thank our speaker again.